It doesn't take a genius to realize that the Earth is in trouble when it comes to energy. The fossil fuels we rely on, coal, oil, and gas, aren't just limited, they're vanishing. Yet they still make up nearly 80% of the energy that powers everything we use: our lights, machines, cars, and even this very device you're using. One day, whether in 100 years or a bit sooner, those sources will run out. And when they do, we'll face a harsh truth. Either we find a new energy source, or we begin to slide backward into a time when life was slow, local, and mechanical. No internet, no smartphones, no global networks. Just fields and plows. If that doesn't sound like the kind of life you'd want to return to, then you're likely in favor of finding something new, something powerful enough to meet the ever-growing energy needs of our modern society. You've probably heard of renewable sources like wind, tidal, or geothermal energy. These are great, but there's a question worth asking. Are we dreaming big enough? Are these ideas enough to carry an energy-hungry civilization into the next century, or even the next millennium? What if the real solution lies in something we've only seen in science fiction? For over 60 years, authors and scientists have been toying with a fascinating concept, an idea so bold and enormous that it almost feels like fantasy. But could this fantasy become reality? Could humanity one day build a Dyson Sphere? And more importantly, how far off are we from making that dream real? I'm Alex McCone, and this is the Astrum Podcast. Today we're diving into the incredible concept of Dyson Spheres, what they are, how they work, and why math might just be the reason they're not only theoretically possible but practically achievable in our future. This all started when I was taking an online course and stumbled upon the topic of Dyson Spheres. Something about the concept grabbed me instantly. It felt massive, ambitious, and yet not entirely impossible. Dyson spheres were originally proposed by a brilliant mind, British-American physicist and mathematician Freeman Dyson, who was thinking about a big question. How would an advanced alien civilization gather enough energy to fuel their ever-growing needs? And how might we detect such a civilization from far away? Dyson imagined that such a civilization, if it had reached a spacefaring level, might not limit itself to solar panels on a planet's surface. Instead, it might go one step further. Build massive orbital structures around its own star to capture the enormous solar radiation it emits. Over time, more and more of these habitats or energy collectors would be built, until eventually, the star would be entirely surrounded. The result would be a gigantic shell, a megastructure that could gather nearly all the energy a star produces. This theoretical structure came to be known as a Dyson Sphere. Freeman Dyson himself got the idea from a science fiction novel called Star Maker, which he openly credited. But unlike the book, Dyson's idea wasn't about fantasy, it was about physics. Because all life, whether human or alien, needs energy to survive. And the more advanced a society becomes, the more energy it consumes. A Dyson Sphere would provide a mind-boggling amount of power, enough to catapult any civilization to the next level on the galactic scale. It wouldn't just be a clever trick, it would be a full transformation of how that society exists. Of course, this sounds like something straight out of a sci-fi movie. The scale alone is overwhelming. We're talking about building something around a star, not a planet, a star, something millions of kilometers wide. By today's standards, the idea seems laughably impossible. Our current technology isn't even close. But maybe that's exactly why we need to consider it more seriously. Because the energy crisis isn't going away. And even if the Dyson Sphere feels distant, the math is telling us something important. We need to look further ahead. Let's look at the numbers. There are currently over 8 billion people living on Earth. Collectively, we use about 4 times 10 to the power of 20 joules of energy each year. That's 400 quintillion joules annually. Sounds like a lot, right? Now compare that to what's left in our known oil reserves. About 6 times 10 to the power of 22 joules. That's around 66 sextillion joules. If we do some basic division, that means we only have around 150 years of oil left. Asterisk at best asterisk. Assuming we keep consuming energy at the current rate. But here's the catch, we're not standing still. We're increasing our energy consumption every single year. And that means we might actually run out of oil even sooner than that 150-year estimate. Sure, we might find a few more reserves here or there, but it's clear they won't last forever. If you're curious, I talk more about this in another video, but for now, let's stay focused on the bigger solution. When we compare fossil fuels to sunlight, things get interesting, really fast. The sun emits an unimaginable amount of energy. Even just the sunlight that reaches Earth's surface is massive. Let's break it down with a simple equation. The sun gives us about 1,360 joules per square meter at this distance. Multiply that by the area of Earth facing the sun, roughly 1.1 times 10 to the power of 14 square meters. Then multiply again by the number of seconds in a year, asterisk asterisk 31,536,000 seconds asterisk asterisk. And the result is a staggering 4.7 times 10 to the power of 24 joules per year. Let that sink in for a second. That's 10,000 times more energy than we currently extract from oil. Just from sunlight. Even if we were only able to capture half of that, it would still be more than enough to power every machine, every home, every car, every city, and even a much larger population than we have today. We're talking about enough energy to support not just 8 billion people, but potentially 40 trillion humans. Of course, with 40 trillion people, energy would be the least of our problems. Where would we even put them all? If we boosted the population by 5,000 times, we'd go from an average of 7 people per square kilometer to 35,000 people per square kilometer. That's one person every 3 square centimeters, an absurd level of crowding that would require the craziest housing solutions imaginable. Floating cities, underground towers, maybe even entire off-world colonies. Still, the point stands, the energy from the sun is plentiful. It's just sitting there waiting to be harnessed. And unlike fossil fuels, it won't run out for billions of years. So the question isn't whether the energy is available, the question is how much of it we can realistically gather and use. Right now we're barely scratching the surface. The sunlight that hits Earth alone is already enough to eliminate our need for fossil fuels, if only we had the infrastructure to gather it efficiently. But as our population keeps growing and as our technology becomes more energy demanding, the day will come when even Earth's surface won't be enough. That's when we'll need to look beyond the planet. And that's where the Dyson Sphere, or more realistically a Dyson swarm, comes in. A Dyson swarm is a variant of the original Dyson Sphere concept. Instead of building one solid structure around the sun, which is basically impossible with current engineering, we send out thousands or millions of solar collectors into orbit around the sun. These collectors could be satellites, panels, or even space habitats, all positioned to capture and relay solar energy. Each unit works individually, but together they act like a gigantic shell, a swarm that grows over time. The beauty of a Dyson swarm is its scalability. You don't need to build the whole thing at once. You can launch a few collectors at first, gather some energy, then use that energy to build and launch more. It's a snowball effect. Over decades or centuries, the swarm expands, giving us exponentially increasing access to solar power. That's the dream. That's the potential. And as I learned in the course I was taking, this kind of thinking is crucial. Because to solve the energy crisis permanently, we can't just think in terms of national grids or carbon taxes. We need to think in astronomical scales. If we can learn how to harness even a fraction of the sun's output directly in space, we would unlock an entirely new era for humanity. An era where energy is no longer a bottleneck, but a launch pad. Now imagine just for a moment, a future where humanity has become so advanced that we can measure our progress not just by our technology or social structures, but by the sheer amount of energy we can harness and use. This idea isn't science fiction. It's actually a scientific framework called the Kardashev scale. It's a method proposed in the 1960s to categorize civilizations based on their energy consumption capabilities. According to this scale, a Type I civilization can utilize all the energy available on its home planet. A Type II civilization takes a giant leap and is able to harness all the energy of its host star, our sun in this case. And a Type III civilization? Well, that's practically godlike. That's a species that can command energy across an entire galaxy. Right now, we're not even at Type I yet. Technically, humanity sits at about Type 0.7. We're not quite able to utilize 100% of Earth's available energy, but we're inching closer as our technologies develop. And here's the exciting part. Constructing a Dyson Sphere or even a Dyson swarm could launch us straight into Type II territory. That's not a small step, it's a monumental leap. It would mean accessing nearly all the energy our solar system has to offer. To put this in perspective, our current global energy consumption stands at roughly 4.7 septillion joules per year. That's an unimaginably large number by everyday standards, but compared to the energy output of the sun, it's laughably small. A Dyson Sphere, once completed, could potentially capture 10 decillion joules of solar energy annually. That's a 20 trillion-fold increase in energy availability. With that kind of power, not only could we keep the lights on, but we could also fuel artificial intelligence, supercomputers, planetary terraforming, interstellar spacecraft, and virtually any other ambitious scientific endeavor imaginable. Surprisingly, the technology to begin building the foundations of such a system isn't entirely out of reach. We already have the capability to create solar panels that can absorb sunlight and convert it into usable energy. Additionally, the idea of placing mirrors or panels in orbit to redirect sunlight back to Earth is something we could realistically attempt with today's engineering. Such structures would need to be in stable orbits and capable of slight reorientations throughout the year to keep their alignment with Earth. But all of that, while complex, isn't outside the realm of current aerospace technology. The real challenge, as you might have guessed, comes down to the materials. Building a shell around the sun, or even a swarm of solar collectors, requires an unimaginable amount of raw material. Just to give you an idea, if we were to build a Dyson Sphere at the same orbital distance as Earth is from the sun, and if we assumed the panels were less than a millimeter thick, we'd still need about 6% of Earth's entire volume in material. That's massive. Even with precision mining, where we only extract exactly what we need, this approach would still be far from practical. After all, we kind of need our planet to remain intact. However, if we consider moving the sphere closer to the sun, perhaps aligning it with Mercury's orbit, things become significantly more manageable. A smaller orbital path means a smaller surface area for the sphere or swarm, and thus fewer materials are needed. In fact, Mercury itself is believed to contain more than enough of the necessary metals and minerals to construct such a structure. Better yet, no one lives on Mercury, at least not yet, so ethical concerns about disturbing ecosystems or displacing inhabitants don't really apply. But even with Mercury's resources, there's another major hurdle: energy. Mining the materials, processing them, manufacturing the solar panels, and then launching those panels into orbit is an incredibly energy-intensive process. And lifting anything out of Mercury's gravity well takes a huge amount of energy due to the planet's relatively deep gravitational field. That's where the problem compounds. Let's say we decided to devote all the solar energy currently hitting Earth, which is about 4.7 times 10 superscript 2 joules per year, toward the sole purpose of lifting Dyson Sphere components out of Mercury's gravity. To get a full Dyson Sphere into orbit, we'd need to overcome the gravitational binding energy of Mercury, which is roughly 2 times 10 superscript 3 joules. Divide that by the energy we can harness annually from sunlight, and you'll see the challenge. It would take us about 425,000 years to finish the job if we rely solely on Earth-collected energy. That's nearly 500,000 years. And during this entire period, we wouldn't be able to use that energy for anything else. Not for powering homes, running machines, or even growing food, because it would all be tied up in Dyson Sphere construction. At this point, the project might sound like a fool's errand. But there's a crucial element we haven't factored in yet: exponential growth. Once the first few solar panels are operational in orbit, they can start providing their own energy to build more panels. Each new panel added increases the total energy output, which in turn speeds up the construction process. Think of it like compounding interest in a bank account. One panel helps create 2, then 4, then 8, and so on. Given enough initial energy to kickstart the process, the growth could become rapid, astonishingly rapid. In fact, using this model of self-sustaining exponential growth, some theoretical calculations suggest that Mercury could be fully dismantled and converted into Dyson infrastructure within just 31 years. That's right, 31 years. That's less than the average human lifespan in many parts of the world. If humanity began construction today, some of us might actually live to see the project completed. It's a mind-boggling idea, but it underscores the core appeal of the Dyson Sphere concept. It's not just a dream. It's something that could, under the right circumstances, become real within a human lifetime. Of course, we'd have to solve an incredible number of engineering and logistical challenges along the way. Mining on Mercury, for instance, would require us to develop entirely new infrastructure, probably remotely operated or AI-controlled mining bots that can function in the harsh, sun-blasted conditions on the planet's surface. And what about transporting materials from Mercury's surface into orbit? We'd need a space elevator, mass drivers, or some other yet-to-be-invented method to launch tens of thousands of payloads into space without burning an unsustainable amount of fuel. These are massive challenges, no doubt, but they are already being seriously considered by engineers and researchers. In fact, the idea of mining operations on the moon is actively being explored right now by NASA, ESA, and private space companies. If we can master it on the moon, Mercury could be next. So once again, what once sounded like pure science fiction might actually become science fact. If humanity survives long enough, and if we maintain a trajectory of technological growth and global cooperation, the Dyson Sphere, or Dyson Swarm, could become not just possible but inevitable. And when that happens, we will no longer be a civilization scraping by with earthbound energy. will be a Type 2 civilization wielding the raw power of a star. Of course, there are also ethical questions to consider. Is it acceptable to completely hollow out an entire planet like Mercury, simply to satisfy our energy demands? Does the end justify the means, especially if there are no living organisms there to suffer the consequences? These are difficult philosophical debates that society would have to grapple with. But as history has shown, when the rewards are high enough, humanity has always pushed forward. Ultimately, the concept of the Dyson Sphere represents something greater than just an engineering marvel. It's a symbol of our potential, a signal to the universe that intelligent life has arrived and has the power to harness the energy of a star. A completed Dyson Sphere would shine brighter in infrared than in visible light, meaning it could be visible to other civilizations across the galaxy. In that sense, it would act as a cosmic lighthouse, announcing our presence to anyone out there watching. And maybe, just maybe, the real reason we should build a Dyson Sphere isn't for the energy. Maybe it's to prove that we can. That we're capable of unity, of ambition, of thinking not just in years or decades, but in centuries. So what do you think? Could you imagine a future where Dyson Spheres are as commonplace as solar farms are today? Maybe our children, or our children's children, will look up at the sun and not see an empty sky, but a shimmering cloud of human ingenuity collecting energy to power worlds beyond. That's all for today's deep dive into the Dyson Sphere. If this has sparked your curiosity, don't forget to follow us for more thought-provoking space content. Until next time, this is Alex McCone signing off from Astrum. Keep looking up, because the future might just be orbiting the sun.